Neptune sits 2.8 billion miles from the Sun. At those distances, it should be dead. Frozen, silent, it has winds faster than any storm on Earth. A storm wider than the entire Atlantic Ocean, just reverse direction. Its clouds vanished completely. Its south pole heated up 20 degrees in 2 years. And the James Webb Space Telescope found a glow coming from the dark side of the planet with no source anyone can identify. We are going inside all of it. The reversing storms, the disappearing clouds, the impossible heat, the glow nobody can explain. If you enjoy the journey, subscribe and leave a like. Brace yourselves. We begin. For most of history, Neptune was the planet scientists filed away and forgot. It sits 2.8 billion miles from the Sun. That is so far out that sunlight arrives there 1,000 times dimmer than it does here on Earth. 1,000 times. Picture standing outside on a bright summer afternoon, then imagine that same sun shrunk down until it looks like a slightly bright star. That is Neptune's entire source of warmth. Scientists had a simple picture of what that kind of distance produces. Cold, slow, dead A-world so far from any energy source that nothing dramatic could possibly happen there. The atmosphere, they figured, would just sit there. Frozen layers stacked on top of each other, quiet winds, maybe a few thin clouds drifting in slow circles. That picture was reasonable. It was logical. And it turned out to be completely wrong. The first major crack in that idea came in 1989. That was the year a spacecraft called Voyager 2 flew past Neptune after a 12-year journey across the solar system. Scientists expected to document a calm, predictable world. Instead, they found the highest wind speeds ever recorded on any planet. Winds ripping across the cloud tops at 1,300 miles per hour. That is faster than the speed of sound on Earth. A commercial airplane flies at roughly 560 miles per hour. Neptune's winds move at more than twice that speed. That alone should have been the headline. A frozen planet generating supersonic winds with almost no energy input from the Sun. But Voyager 2 kept going, and what it found next was even harder to explain. There was a storm, a massive dark oval spinning in the northern atmosphere. Scientists named it the Great Dark Spot. It was wide enough to drop the entire continental United States inside it with room to spare. And it was moving, swirling, alive. A year later, when astronomers pointed the Hubble Space Telescope at Neptune to follow up, the Great Dark Spot was gone. Completely gone. Vanished between observations. No wreckage. No sign it had ever existed. A storm bigger than a continent had simply disappeared. That vanishing act did something important to the scientific community. It forced researchers to admit they had no working model for Neptune's weather. On Earth, we can trace a hurricane from birth to death. On Jupiter, the Great Red Spot has been spinning for hundreds of years. On Neptune, a storm the size of a country appears and disappears between telescope sessions. The rules do not apply there. And what came next, over the following decades, pushed the mystery even further. Scientists kept watching. They kept collecting data. And every few years, Neptune did something that broke whatever model they had just built. Temperature readings came back wrong, cloud layers appeared and then vanished entirely. Storms moved in directions that violated known atmospheric physics. Each anomaly could have been a glitch. One strange reading in a dataset is easy to dismiss. But the anomalies kept stacking up. By the time modern telescopes started focusing on Neptune with real precision, the picture was clear. Something on this planet is generating energy, behavior, and activity that has no explanation inside our current understanding of planetary science. The frozen, boring planet at the edge of the solar system is alive. And whatever is driving it, we are only beginning to understand the scale of it. The first major clue starts with the wind. Stand outside in a Category 5 hurricane, and the wind tries to rip you off your feet at about 180 miles per hour. Scientists consider that the outer limit of what Earth's atmosphere can produce. Neptune's winds hit 1,300 miles per hour. Imagine standing on Neptune's cloud layer. The wind would carry you around the entire planet in about 16 hours. That is a lap around a world 30,000 miles wide at the equator, completed in less than a day. The number is confirmed by direct measurement, and it raises a question atmospheric scientists have been arguing about for decades. Where is the energy coming from? On Earth, the answer is simple. The sun heats the surface unevenly, hot air rises in the tropics, cold air rushes in from the poles, pressure differences build and then release as storms and wind. The whole system runs on solar energy. Neptune gets almost none of that. The sun out there is 1,000 times weaker than it is on Earth. By the laws of atmospheric physics used for every other planet, Neptune's weather engine should barely be running. The atmosphere should drift slowly. The winds should be light. Astronomers spent years trying to make that math work. They adjusted variables. They accounted for differences in Neptune's composition, which contains hydrogen, helium, and traces of methane. Nothing made the numbers add up. The leading idea is that the heat is coming from inside the planet. Neptune radiates significantly more energy outward than it absorbs from the sun. Something deep inside generates warmth, and that warmth pushes up into the atmosphere and drives the circulation. The internal heat engine keeps Neptune's weather alive. But that explanation raises its own problem. Scientists can observe and measure the heat output. What they cannot do is identify the source with certainty. Ice giants are not supposed to have the kind of radioactive decay or gravitational compression that powers gas giants like Jupiter. The interior should be cooling slowly, like a rock heated long ago and simply shedding warmth over time. The amount radiating outward is far higher than that model predicts. Something is wrong with the model. Or something is happening inside Neptune that nobody has classified yet. Meanwhile, the wind keeps spinning, 1,300 miles per hour at the cloud tops, faster at some latitudes, slightly slower at others. Bands of wind shear in opposite directions, tearing at each other along the boundaries. The whole cloud layer is in a state of constant, violent churn. And here is the detail that makes it stranger still. The fastest winds on Neptune blow in the opposite direction of the planet's rotation. Earth's strongest winds move with its rotation. Neptune's punch back against it. Scientists call this retrograde wind flow. And on Neptune, it reaches speeds that no atmospheric model predicted or fully accounts for. 1,300 miles per hour, in the dark, 3 billion miles from the sun. Powered by something buried deep inside a planet we have never sent a probe to orbit. The wind is real. The source is a mystery. And the storms it builds are unlike anything else in the solar system. The year was 1989, and Voyager 2 was making its final planetary flyby after more than a decade in space. The spacecraft had already visited Jupiter, Saturn, and Uranus. Each encounter delivered surprises. But Neptune, the last stop, was the one that scientists would talk about for decades. When the cameras turned toward the planet's blue face, there it was. A massive dark oval spinning in the southern hemisphere, wide enough to swallow the United States whole. Scientists called it the Great Dark Spot. From the images, it looked almost familiar. Jupiter has its Great Red Spot, a storm that has been spinning for centuries. Scientists assume Neptune's dark storm was something similar. A long-lived atmospheric feature, a permanent fixture of the planet's personality. They were wrong. When the Hubble Space Telescope trained its lenses on Neptune in 1994, 5 years after Voyager 2's visit, the Great Dark Spot was gone. The exact location where a continent-sized storm had been raging showed clear blue sky. No remnants, no swirl of fading clouds, nothing at all. This was alarming. On Jupiter, a storm that size would persist for hundreds of years. On Earth, even the most powerful hurricane takes weeks to fully dissolve. A storm the size of a country should leave some trace, some residual disturbance in the atmosphere. Neptune's great dark spot left nothing behind. Scientists began building a theory. Unlike Jupiter's storms, which are powered by rising columns of warm gas from deep in the atmosphere, Neptune's dark spots may be atmospheric disruptions near the cloud tops. When conditions shift even slightly, the disruption loses its anchor and collapses. The whole structure unravels within months. But the Hubble telescope did not find empty sky where the great dark spot had been. It found a new dark spot. A different one. Smaller. Located in the northern hemisphere rather than the south. A second storm had appeared while the first one was dying. Neptune cycles through dark spots the way Earth cycles through seasons. Old ones vanish, new ones form somewhere else, and each one grows large enough to cover multiple American states before eventually collapsing. Here is what makes that unsettling. Scientists cannot predict when or where the next one will form. They cannot model the conditions that trigger the appearance of a new spot. Each one has shown up without warning in telescope data, already fully formed and spinning. In 2015, Hubble spotted another dark vortex. In 2018, yet another appeared. The pattern continued, each storm living for months to a few years before disappearing. And with each new observation, researchers discovered something unexpected. The dark spots are not windows through the cloud deck the way scientists originally assumed. They are not holes where you can see deeper into the atmosphere. A team using the European Southern Observatory figured out that the dark regions are actually places where the atmosphere itself changes chemistry. Air at those depths contains particles that interact differently with light, making the region appear darker from space. The darkness is a symptom of something happening inside the storm structure, not a gap in the clouds above it. Which means every time a dark spot vanishes, something is happening to the chemistry of Neptune's atmosphere in that region. Something is shifting. And whatever causes that shift is still unidentified. Something even stranger happened to one of those later storms. Instead of dying, it turned around. In 2015, Hubble spotted a dark vortex forming in Neptune's northern hemisphere. Scientists had seen this before. A dark storm appears, drifts toward the equator over the following months, reaches the low latitudes, and breaks apart. That was the pattern. Every dark spot on record had followed some version of it. The equator acts like a drain, pulling the storm in and tearing it to pieces as atmospheric conditions change at lower latitudes. Scientists watching the 2015 storm expected the same ending. They tracked it as it drifted southward. It was moving at the right speed, in the right direction. The storm was heading toward the equator, and by every model they had, it was going to die there. Then, in January of 2020, something changed. The Hubble Space Telescope captured images showing the storm had stopped. It had halted its southward drift and reversed course. The vortex was now moving north, back the way it came, away from the equator. In the entire history of planetary observation, across every planet scientists had ever studied, no one had ever seen a storm do this. Atmospheric researchers were caught completely off guard. On Earth, storms are pushed around by jet streams and pressure systems. They turn, slow down, and speed up based on the flow of air around them. But a storm reversing its overall migration direction, heading back north after months of moving south, is not something any model predicted as possible. The forces that were supposed to pull it toward the equator had somehow reversed their grip on it. And then the storm did something else. While it was turning around, the dark vortex spawned a smaller companion. A second dark spot appeared right next to the main storm, circling it like a satellite. Scientists had seen companion features form near dark spots before, but the timing was striking. The reversal and the birth of the companion happen nearly simultaneously. The leading idea is that the reversal happened because the storm reached a depth in the atmosphere where wind conditions changed sharply. The Coriolis effect, the same force that spins weather systems on Earth, behaves differently at different atmospheric pressure levels on Neptune. If the storm descended into a zone where the flow was reversed, it could theoretically get pushed back toward the pole. The problem is that scientists cannot confirm this. They cannot see inside the storm. They cannot measure what is happening at the depths where the reversal may have occurred. The model is plausible. It fits some of the data. But it is not proven, and no simulation has fully reproduced what Hubble observed. What is confirmed is the reversal itself. The Hubble images are clear. The storm stopped, turned, and headed north. After several more months of observation, scientists watched both the main storm and its companion gradually fade. By the time Hubble checked again, they were gone. But the question the reversal left behind is enormous. If a storm can reverse its migration path, it means the atmospheric forces that control storm movement on Neptune are more complex and more variable than any current model accounts for. It means storms can survive longer than predicted, by finding new atmospheric pockets to anchor in. And if the reversal can happen once, it can happen again. A storm could theoretically reverse multiple times, bouncing between latitudes, surviving for far longer than expected. The atmosphere of Neptune is capable of behavior that planetary science has no formula for. And the reversal was only the beginning of what recent observations have uncovered. The companion vortex that formed beside the reversing storm was easy to overlook. The main event was the reversal. A continent-sized storm turning back toward the north grabbed every headline. The smaller dark oval that appeared next to it got a footnote in most reports. But scientists who study Neptune's atmosphere closely knew the companion mattered just as much as the U-turn. Here is why. Dark vortices on Neptune are enormous atmospheric structures. They take significant time and energy to build. The conditions have to align just right, specific pressure levels, the right temperature gradient, the correct wind shear between atmospheric layers. You cannot rush the process. On Earth, even a tropical storm takes days to organize before it becomes a hurricane. A storm the size of a small continent should take far longer. The companion appeared in a matter of weeks. Scientists watching the Hubble images saw the smaller dark oval materialize alongside the parent storm during the reversal period. It was spinning independently. It had its own structure, and it looked fully formed, as if it had been building somewhere beneath the visible cloud layer and only surfaced when the larger storm disrupted the atmosphere around it. One possibility researchers considered is that the parent storm's reversal created a pressure disturbance in the surrounding atmosphere. A sudden change in the movement of a structure that massive would send shockwaves through the surrounding gas. Those disturbances could compress nearby regions of the atmosphere, triggering the rapid formation of a new vortex nearby. If that is true, it means Neptune's atmosphere responds to its own storms in ways that amplify the chaos. One storm does not simply die. It can give birth to another one while it is reversing direction, passing some kind of atmospheric torch before fading out. This is completely unlike anything seen on Saturn or Jupiter. On those planets, storms are more isolated. A vortex on Jupiter can spin for centuries without spawning companions the way Neptune seemed to. The behavior points to a fundamentally different atmospheric structure. Neptune's weather does not follow the same playbook as the gas giants. The companion vortex faded alongside the parent storm over the months that followed. But researchers kept looking at the data, trying to understand whether the companion was a regular feature of Neptune's dark spots, or something unique to this particular event. What they found in historical Hubble images was both reassuring and strange. Several past dark spots had also shown bright, white companion features alongside them. Those companions, however, were made of methane ice clouds, not dark atmospheric material. They appeared bright instead of dark. They formed because the storm's circulation lifted gas from lower in the atmosphere up to colder altitudes, where it froze into visible clouds. The 2020 companion was darker. It behaved more like a second vortex than a simple cloud feature. That distinction matters, because it suggests Neptune's storms can interact with each other and produce offspring through at least two different mechanisms. One known, one newly observed, two mechanisms, two different kinds of offspring, and scientists still cannot fully predict when either one will occur. The atmosphere of Neptune is running on a logic that our models are still trying to catch up to. And while researchers were puzzling over these storm births and reversals, they were also getting their first clear look at what dark spots are actually made of. What they found inside those storms overturned a 30-year-old assumption. For 30 years, scientists had a working explanation for Neptune's dark spots. The assumption was straightforward. The spots were holes, gaps in the bright upper cloud layer where the clouds had thinned out or cleared away entirely. From space, looking down through that gap, you would see the deeper, darker atmosphere below. The darkness was depth, not chemistry. It was a reasonable idea. It fit the images. It matched what scientists understood about cloud dynamics on other planets. And it was wrong. In 2023, a team using the European Southern Observatory's Very Large Telescope in Chile did something that had never been done before. They observed a Neptune dark spot from the ground. Previous observations came from space-based telescopes like Hubble. Studying these features through Earth's atmosphere was considered nearly impossible, because the resolution required to separate Neptune's atmospheric details is extreme. Neptune is so far away that it appears as a tiny disk in even the best ground-based telescopes. But the Very Large Telescope, using advanced optics that cancel out atmospheric blurring in real time, pulled it off. The team analyzed the light coming from the dark spot in detail. They broke it down by wavelength, studying how the dark region absorbed and reflected different colors of light. The result demolished the old assumption. The dark region was not a clearing. The upper cloud layer was still present. The clouds had not thinned out or disappeared. Instead, the air inside the dark spot contained particles that were chemically different from the surrounding atmosphere. These particles were absorbing more light across a wide range of wavelengths, making the entire region appear darker, without any gap in the clouds above. Scientists believe these particles form when air from the lower atmosphere, below the main visible cloud deck, gets pushed upward into the haze layer above. Down there, the chemistry is different. The pressure is higher. The temperature changes sharply with depth. When that deep air rises and mixes with the haze layer above, the particles darken. The whole region of mixed atmosphere then appears as a dark oval from space. That overturns the entire picture. Dark spots are not windows into Neptune's depths. They are places where the atmosphere is mixing vertically in an unusual way, dragging up chemistry from below and changing the optical properties of the haze layer above. This matters enormously. If dark spots are vertical mixing events rather than surface clearings, then they are symptoms of deep atmospheric circulation. Something down below is pushing material upward with enough force to alter the chemistry of a region wider than a continent. That force is coming from inside the planet, from layers scientists have never directly observed. It also raises a new question. If dark spots are driven by upwelling material from below, what is triggering the upwelling in the first place? What disturbs the deep atmosphere enough to send a column of gas surging upward through hundreds of miles of pressure until it reaches the visible cloud layer? Nobody knows. What the team did notice, right next to the dark spot they were studying, was something completely unexpected. A bright white patch of cloud sitting immediately adjacent to the dark oval, brighter than any other feature on the visible disk. It was not the kind of companion feature scientists had catalogued before, and it was doing something strange. The bright white cloud appeared right beside the dark spot, sitting on its southern edge like a spotlight in the dark. Scientists had seen bright features near dark spots before. Past observations showed wispy methane ice clouds forming close to the edges of dark vortices. The explanation was clean and well understood. A dark storm's circulation forces air upward near its borders. That rising air carries methane gas into colder, higher altitudes. At those cold heights, the methane freezes into tiny ice crystals. Those crystals form a cloud that looks white and bright from space. Physics doing what physics does. The white companion discovered in 2023 was different. The Very Large Telescope team analysed it carefully. They studied its location relative to the dark spot, they measured how it reflected light at different wavelengths, and they found something the methane cloud theory could not explain. The feature was sitting south of the dark spot, on the inner edge of the vortex boundary. Methane ice clouds typically form on the outer edges of dark spots. The placement was wrong. On top of that, the way this cloud reflected light across different wavelengths did not match the signature of methane ice. The spectral fingerprint was different. The composition appeared to involve a mix of particles that corresponds to no known companion cloud formation. The team was left with a confirmed observation and no confirmed explanation. One idea researchers proposed is that the white patch forms from a different process entirely. As the dark spot circulation pulls deep atmospheric material upward, the upwelling jet might be strong enough to push through multiple cloud layers and create a dense, highly reflective patch at a specific altitude. The brightness would come from the density of the cloud particles, compressed into a narrow band by the mechanics of the storm below. Another idea suggests the bright region is a shear zone. Where the dark spot's edge meets the surrounding atmosphere, wind speeds change rapidly. That rapid change in speed creates intense compression in a narrow band of air. Compressed air carries more particles per unit of space. More particles per unit of space means a brighter, more reflective region. Neither idea has been confirmed. Both are plausible. Scientists admit that the atmosphere may be doing both things at once, producing bright companions through overlapping mechanisms depending on the depth, temperature, and chemistry of each individual storm. That uncertainty is itself meaningful. Scientists have been watching Neptune's dark spots since 1989. Decades of observation, and they still cannot predict what a given storm will produce alongside itself. Each new observation returns with something slightly unexpected. The timing of this discovery added an extra layer of strangeness. The same year this observation was made, separate research using 3 decades of archival telescope images revealed something hiding in plain sight. Something that connected Neptune's behavior not just to its own internal dynamics, but to the Sun itself. That discovery changed the conversation entirely. Researchers had spent months focused on the storms, the dark spots, the companions, but the data sitting in archival telescope images pointed to something happening at a planetary scale. Something affecting every inch of Neptune's visible face. The entire cloud layer of the planet had disappeared, and the Sun may have been the one that took it. Astronomers noticed it gradually at first, then all at once. A team of researchers decided to compile every available telescope image of Neptune taken over the previous 30 years. Images from Hubble, images from large ground-based observatories, infrared data, visible light data. They built a timeline of the planet's appearance spanning 3 decades, from the early 1990s all the way to the early 2020s. In the early images, Neptune looked the way it always had in textbook photos. A rich, deep blue disk decorated with bright, wispy streaks across its face. Those white features were clouds. Specifically, they were methane ice clouds forming at the top of the troposphere, where the atmosphere is cold enough to freeze methane into crystals. Scientists called them cirrus-style clouds because they looked similar in structure to the thin, high-altitude ice clouds you see on Earth, though they were made of frozen methane instead of frozen water. The clouds were not unusual. They had been observed consistently across decades of data. They were considered a permanent feature of Neptune's upper atmosphere. When the team reached the images from 2019 and 2020, the clouds were gone. All of them. The entire layer of high-altitude methane ice clouds had faded away. The planet's face, stripped of its white streaks, looked like a plain blue marble. No wispy features, no bright patches, just smooth, unbroken blue. The disappearance was not gradual in the way you might expect from a slow seasonal change. It happened over a relatively short window. The clouds were present in significant quantities, then they were gone. The planet had shed its visible cloud layer almost entirely. Scientists had no ready explanation. A global loss of methane ice clouds across an entire planetary atmosphere is a massive event. The mass of frozen material that simply stopped forming represents an enormous atmospheric change. And Neptune's cloud layer had been stable across all prior observation data. The team dug deeper into the timeline. They looked at every year, every season, every instrument used to capture Neptune's cloud coverage. And they found a pattern buried inside 3 decades of data. Neptune's cloud abundance was changing in sync with something. The peaks in cloud coverage matched up with specific periods in the Sun's 11-year activity cycle. The troughs, including the dramatic disappearance seen in 2019 and 2020, corresponded to different points in that cycle. The clouds seemed to be responding to solar activity from 2.8 billion miles away. But there was a delay. 2 years. The solar cycle peaked, then about 2 years later, Neptune's clouds responded. 2.8 billion miles away, with a 2-year lag, Neptune's upper atmosphere was somehow reacting to what the Sun was doing. Scientists had no confirmed mechanism to explain that delay or that connection. The leading idea involved ultraviolet radiation from the Sun triggering chemical reactions in Neptune's upper atmosphere, building the chemical precursors needed to form methane clouds. But how that process works across that distance, with that specific delay, has no confirmed answer. The clouds came back partially in 2023, but the episode left researchers with a disturbing question. If Neptune's atmosphere can lose its entire cloud layer in response to solar cycles, what else is the planet's atmosphere capable of losing? And what is happening to the temperature while the clouds disappear? 2.8 billion miles of empty space separates Neptune from the Sun. At that distance, the sunlight arriving at Neptune carries about 900 times less energy than what hits Earth. Scientists have always treated Neptune as essentially independent of solar influence when it comes to weather. Too far away. Too little energy input to matter. That assumption cracked open when researchers examined the cloud disappearance data more carefully. The pattern was undeniable. Neptune's cloud coverage appeared to track the Sun's 11-year activity cycle. When solar activity was high, the cloud layer was thick. When solar activity dipped into a minimum, the clouds began thinning. And when the planet's cloud cover hit its lowest point in 2019 and 2020, the Sun was approaching a period of reduced activity. The 2-year delay between solar peak and Neptune cloud response made the connection even harder to dismiss. A random correlation would not show a consistent delay of almost exactly 2 years across 3 separate solar cycles worth of data. Something physical was producing that lag. The leading proposal among atmospheric scientists centers on ultraviolet radiation. The Sun emits ultraviolet light constantly, and the intensity fluctuates with the solar cycle. When solar activity increases, more ultraviolet radiation streams outward in all directions. Some of that radiation eventually reaches Neptune's upper atmosphere. The idea is that ultraviolet light drives chemical reactions in Neptune's stratosphere. Specifically, it may break apart certain molecules and reassemble them into the chemical building blocks needed to form methane ice clouds. When the ultraviolet supply is high, cloud formation gets a boost. When it drops, the chemical engine slows and the clouds thin out. The 2-year delay might represent the travel time for that chemical process to complete itself. The ultraviolet signal arrives, the chemistry begins, the clouds eventually appear or disappear based on whether the process is building up or winding down. Each step takes time. 2 years worth of time, apparently. But researchers are quick to say that this is a working hypothesis. The chain of chemical events that would produce this specific response at this specific timescale has not been confirmed in a laboratory or validated through direct atmospheric sampling. Scientists know what the data shows, they know the correlation is real. How the mechanism actually works at the molecular level remains an open problem. And the implication of this discovery extends beyond Neptune. Every planet with an atmosphere that receives ultraviolet radiation from the sun could theoretically show this kind of delayed solar response. If Neptune's entire cloud layer can appear and disappear on a sun-driven chemical schedule from nearly 3 billion miles away, what might be happening to cloud formation on other worlds we have not yet studied in this kind of detail? It also raises a practical concern. If cloud formation on Neptune is sensitive to solar activity cycles, then during solar minimums, the planet loses its reflective cloud layer. A planet with fewer reflective clouds absorbs more incoming energy, even if that energy is minimal. That change in energy balance could drive the kind of temperature swings that researchers began noticing in the thermal data. Because while the clouds were vanishing, something extraordinary was happening to the temperature. Something that broke every model scientists had for how ice giants heat and cool over time. Scientists began taking precise temperature measurements of Neptune's stratosphere in the early 2000s, using infrared telescopes that could detect the heat radiating off the planet's upper atmosphere. The stratosphere sits well above the clouds. On Neptune, it acts as a thermal cap, and measuring its temperature gives scientists a way to track changes in a planet's energy balance over time. The readings coming back from Neptune starting in 2003 showed a steady drop. Year after year, the stratosphere was getting colder. Slowly but consistently, the thermal readings declined over more than a decade. By 2018, the stratosphere had cooled by 14 degrees Fahrenheit compared to where it started. 14 degrees of change in a planetary stratosphere over 15 years represents a massive shift in the energy being radiated from that layer. On Earth, a change of that scale across the entire stratosphere would be considered a global emergency. Scientists tried to explain it. The most logical candidate was seasonal change. Neptune takes 165 years to complete one orbit around the Sun, and its seasons last for decades. A cooling of 14 degrees over 15 years could theoretically fit a slow seasonal cycle. The problem is the timescale. A seasonal cooling driven by an orbit that takes 165 years should be nearly invisible across just 15 years. The movement around the Sun is so slow that seasonal temperature changes should happen on a glacial pace. 14 degrees in 15 years is far too fast for a seasonal explanation to cover. Something was pulling heat out of Neptune's stratosphere faster than its orbital position could explain. The cooling was real. The cause had no clean answer. Then, in 2018, the trend stopped. The drop that had been steady for 15 years simply halted. And within 2 years, the temperature began rising, recovering some of what it had lost. A planetary stratosphere that cools for 15 years and then rebounds in 2 does not behave like a system governed by slow, century-scale orbital mechanics. Something operating on a timescale of years was influencing Neptune's energy budget. Researchers considered whether the solar cycle could be responsible. The sun's activity shifts on an 11-year rhythm. If Neptune's atmosphere is sensitive to that rhythm, as the cloud disappearance data suggested, then stratospheric temperatures could track the solar cycle with some delay. Plausible, but the scale of the swing, 14 degrees from a sun 1,000 times weaker than the one above Earth, is larger than straightforward solar forcing should logically produce. Which brings the explanation back to the interior. If Neptune's internal heat output is variable, producing irregular pulses rather than a steady constant flow, then stratospheric temperatures could rise and fall on timescales driven from inside the planet rather than from the sun above. A 15-year cooling phase, followed by a rapid rebound, would fit an interior that reduced its heat output for a stretch and then surged again. Scientists cannot directly measure Neptune's internal heat flux. They can only observe the atmospheric results. And those results point to a planet whose energy budget is controlled by something inside it that operates on irregular and unpredictable timescales. If the stratosphere alone was producing these anomalies, researchers might have found a way to contain the mystery. But the stratosphere was only half the story. At the same time, the global atmosphere was cooling. One specific part of the planet was doing something that shattered every remaining expectation. The South Pole suddenly heated up. Neptune's South Pole should be cold. The planet orbits so far from the sun that even direct sunlight delivers almost no warmth. The South Pole had been receiving its weak share of that sunlight for several decades, given the tilt of Neptune's axis and the slow crawl of its seasons. Researchers expected modest, gradual warming, consistent with the pole receiving sunlight during a long seasonal cycle. What the thermal imaging revealed between 2018 and 2020 was a temperature spike of 20 degrees Fahrenheit in roughly 2 years. 20 degrees. In 2 years. At the South Pole of Neptune. Picture the Arctic on Earth suddenly warming 20 degrees in 2 years with no change in sunlight, no identifiable external cause. Scientists would call that a catastrophic anomaly. On Neptune, the South Pole pulled that off in a region that receives a fraction of the energy the Arctic does. The spike was captured through thermal imaging using multiple large telescopes. Different instruments confirmed the same reading. It had no precedent in any planetary observation database. The timing made it stranger. The stratosphere as a whole had just spent 15 years cooling down by 14 degrees. While that cooling was completing, one specific part of the planet heated up by 20 degrees. Global cooling alongside localized polar heating. Both events occurring on the same planet at nearly the same time, pointing in opposite directions. No known mechanism can produce these two events simultaneously. Seasonal change cannot explain them. The planet's slow orbit does not generate energy shifts fast enough. Solar input at that distance cannot create a polar heating event of that magnitude in 2 years. The ideas researchers have discussed range from internal heat pulses to unusual atmospheric circulation that funnels energy toward the pole in concentrated bursts. One suggestion is that the same vertical mixing process that creates dark spots could be operating at the pole, pushing warm material from the deep atmosphere upward through that specific region. A plume of warmer gas rising from the interior could temporarily heat the polar stratosphere above it. That idea is consistent with some of the data. It is also completely unconfirmed. What the South Pole heating event did was remove the last possibility of a simple explanation. Scientists had been trying to find a single cause for Neptune's strange behavior. A mechanism that could connect the reversing storms, the vanishing clouds, the stratospheric cooling. The polar heating event made clear that whatever is happening on Neptune is not one thing. Multiple, unusual processes are operating simultaneously, in different layers, in different regions, producing contradictory effects at the same time. Neptune is running several unexplained experiments on its own atmosphere at once, and each one feeds data into a picture that no existing model can assemble into a complete explanation. The South Pole heating event has pushed the scientific community to seriously consider something once thought impossible. If heat is rising from inside the planet in concentrated bursts, then Neptune's interior is active in ways that ice giant formation models have never accounted for. All of this atmospheric chaos sits above an interior that, when scientists began measuring it properly, turned out to be hiding something even stranger underneath. Neptune's seasons are the longest in the solar system. One full orbit around the Sun takes 165 Earth years. Because of the tilt of Neptune's axis, each pole spends roughly 40 years pointed toward the Sun. Then, roughly 40 years pointed away. 40 years of polar summer, 40 years of polar winter. When Voyager 2 flew past Neptune in 1989, the southern hemisphere was in the middle of a long summer. The South Pole had been soaking up sunlight by Neptune standards for decades. Scientists expected that slow seasonal exposure to gradually warm the southern regions and cool the northern ones. They expected the change to move like a glacier. Slow, predictable, the reality was something else. The polar heating event between 2018 and 2020 happened during what should have been a gradual transition away from southern summer. The South Pole was beginning to turn away from the sun. Temperatures, by seasonal logic, should have been starting to drop or stay flat. Instead, they surged by 20 degrees in 2 years. The 15-year cooling trend in the stratosphere does not map cleanly onto the seasonal timeline either. The cooling began around 2003 and ended around 2018. That window does not correspond to any obvious seasonal phase. No major orbital milestone crossed during that time could explain a prolonged global cooling trend. Scientists who model seasonal change on giant planets use something called a radiative timescale. This is essentially how long it takes a planet's atmosphere to respond to changes in incoming sunlight. On Earth, the radiative timescale is short. The atmosphere responds to sunlight changes in weeks. On Neptune, the stratosphere's radiative timescale is estimated to span several hundred years. Seasonal temperature changes should occur on a timescale of centuries. That estimate makes the temperature events even harder to understand. A stratosphere with a several hundred-year response time should not show 14 degrees of cooling in 15 years. And it should not produce a 20-degree polar spike in 2 years. The numbers are off by orders of magnitude from what the radiative timescale model predicts. Either the model is wrong, or something beyond seasonal mechanics is driving Neptune's temperatures. The most serious proposal involves the planet's internal heat. If Neptune's core is releasing irregular pulses of heat into the atmosphere above it, those pulses could drive temperature changes on timescales far shorter than seasonal mechanics would predict. The atmosphere would respond to the planet's own interior rather than to the distant sun. The interior does not move on a 40-year seasonal schedule. It moves on whatever rhythm is happening deep inside. And the interior of Neptune, when scientists began examining it through gravitational measurements and magnetic field mapping, turned out to be structured in a way that nobody had expected. A way that makes irregular heat output not just possible, but maybe inevitable. Neptune is the only ice giant close enough to study in this kind of detail. What scientists learn from its broken seasonal patterns will directly shape how they interpret the atmospheres of worlds they will never be able to observe up close. The seasonal data alone would be enough to make Neptune the most puzzling planet in the solar system. But the seasonal mystery is just the atmospheric layer. What the magnetic field data and the gravitational readings began revealing about the planet's interior pushed the strangeness far deeper. Every planet with a molten or electrically conductive interior generates a magnetic field. Earth's field is produced by its spinning liquid iron outer core. Jupiter's field comes from a deep layer of hydrogen compressed until it conducts electricity like metal. The field wraps around the planet in a shape roughly aligned with the rotation axis, slightly tilted, maybe 10 or 15 degrees, but broadly symmetrical. That is the pattern for almost every planet in the solar system. Neptune's magnetic field does not follow that pattern. The field is tilted by about 47 degrees relative to Neptune's rotation axis. For comparison, Earth's magnetic field is tilted by roughly 11 degrees, and scientists consider even that modest tilt a topic of ongoing research. Neptune's 47-degree tilt is extreme. The magnetic North Pole does not point anywhere near the planet's geographic North Pole. A compass on Neptune would lead you far astray. But the tilt is only part of the strangeness. The other part is the origin point. On Earth, Jupiter, and Saturn, the magnetic field emerges from deep inside the planet near the center. The source region is close to the core. Neptune's field originates from a point that sits significantly off-center. The magnetic source region is located closer to the planet's surface than to the core, displaced to one side of the interior. This is called an offset dipole, and Neptune has one of the most extreme examples ever measured. Scientists who study planetary magnetism have a standard model for how magnetic fields form inside planets. The model requires a specific type of electrically conductive fluid moving in a specific way inside the planet's interior. For the field to be this tilted and this off-center, the conductive layer generating it must be sitting at an unusual depth and moving in an unusual pattern. The leading explanation is that on ice giants like Neptune, the electrically conductive layer is made of water and ammonia under extreme pressure. At the pressures found in Neptune's interior, water does not stay liquid in the normal sense. It enters a state where it conducts electricity readily. This pressurized conductive water layer could be generating the field. For the field to be this tilted and off-center, the conductive layer must be highly irregular. Rather than forming a smooth, globe-wrapping shell, it likely exists in patches or uneven regions, generating the field in lopsided and asymmetric ways. That kind of irregular internal structure would produce exactly the kind of offset tilted field that scientists measure from space. The strange magnetic field is a symptom of a strange interior. And if the interior conducting layer is irregular and patchy, then the movement of material through that layer is also irregular. Heat flowing through an uneven conductive region would not distribute itself smoothly through the planet. It would channel through some areas and accumulate in others. That uneven heat distribution, rising from an irregular interior, could produce exactly the kind of localized temperature spikes and unexpected atmospheric behavior that scientists have been measuring on the surface. The magnetic field is pointing to something deep inside Neptune that has never been directly measured. And when scientists looked at the gravitational data, what they found inside the core made the magnetic picture look simple by comparison. Scientists cannot see inside Neptune. There is no drill, no probe, no instrument that can reach through thousands of miles of pressurized gas and ice to directly sample the planet's interior. What they can do is measure gravity. As Neptune orbits the Sun, its gravitational pull tugs on distant objects in subtly different ways, depending on how its mass is distributed inside. A planet with a perfectly uniform interior would produce a smooth, symmetrical gravitational signature. A planet with lumpy, uneven mass distribution produces a gravitational signature with small but measurable irregularities. Researchers analyzed the gravitational data collected over decades of observation, including data from the Voyager 2 flyby and subsequent telescope measurements. What the data showed was a core that does not match the standard model of an ice giant interior. The standard model assumes that Neptune has a rocky, icy core roughly the size of Earth at its center, surrounded by a deep layer of water, methane, and ammonia ice under extreme pressure, then topped with a gaseous atmosphere. The core should be relatively uniform, a dense, compressed sphere of rock and ice sitting at the center of the planet. The gravitational readings suggest something different. The mass distribution inside Neptune appears uneven. There are regions of higher density scattered in irregular patterns throughout the interior. The core does not behave like a smooth, uniform sphere. It behaves like something with dense pockets and less dense regions, arranged in a pattern that does not follow any simple symmetric shape. This irregular mass distribution points to processes inside the planet that a simple, static core cannot explain. A uniform core just sits there. An irregular core with dense pockets and uneven distribution implies that material inside Neptune is moving, or has moved, in ways that sorted heavier and lighter material into different regions. One proposal is that Neptune's interior is experiencing a form of differentiation, a process where gravity causes heavier materials to sink and lighter materials to rise over very long timescales. If this process is still ongoing, material inside the planet is actively redistributing itself. That redistribution would release gravitational energy as heat. Heavy material falling toward the center converts potential energy to thermal energy. That thermal energy would then radiate upward through the planet's layers, contributing to the excess internal heat output that scientists measure at the surface. A second, more dramatic proposal suggests that tectonic or volcanic activity is occurring deep inside Neptune. Not the kind of plate tectonics that reshapes Earth's surface over millions of years, but deep interior fractures and movements that shift dense material around and release stored heat in bursts. This was once considered impossible for an ice giant. Ice giants were thought to be geologically dead, their interiors too cold and too compressed for any active internal geology. The gravitational data suggests that assumption may need revision. If Neptune's interior is not static, if material is moving, and heat is being released in irregular bursts, that would explain a great deal about what the atmosphere is doing. The excess heat output, the unexpected temperature spikes, the irregular atmospheric behavior. But there is one more piece of evidence that makes the volcanic idea harder to dismiss than any gravitational reading alone. And it comes from the planet's south pole. The idea of volcanic activity inside an ice giant sounds like the setup to a science fiction story. Neptune is a world made mostly of water, ammonia, and methane under conditions of extreme pressure. Its surface temperature hovers around negative 328 degrees Fahrenheit. The very concept of volcanic activity on such a world runs against everything intuitive about the planet. But the evidence has been piling up in a direction that makes active internal geology increasingly difficult to rule out. Start with the gravitational anomaly. The irregular mass distribution inside the planet, with its dense pockets scattered throughout the interior, is consistent with a world where material has been displaced by some kind of internal geological process. Static cores do not redistribute material into irregular clusters on their own. Add to that the excess heat output. Neptune radiates significantly more energy outward than it receives from the Sun. The exact ratio is debated, but scientists agree that the surplus is substantial. Some of that surplus could come from the slow cooling of the planet's formation heat, energy stored from 4.5 billion years ago when Neptune first formed from collapsing gas and rock. But models of how quickly that stored heat should dissipate suggest the planet should have cooled faster than the measured output implies. Something is either slowing the cooling or adding fresh heat to the system. Then, add the South Pole temperature spike. 20 degrees of warming in 2 years, in a region beginning to move away from the Sun. If the heat is not coming from outside the planet, it is coming from inside. A pulse of heat rising from the interior through the atmosphere and concentrating at the South Pole is one of the few mechanisms that could produce that specific pattern. Some researchers have proposed a process called superionic water as a partial explanation. At the pressures found deep inside Neptune, water enters a strange state where the oxygen atoms lock into a crystal structure, but the hydrogen atoms break free and move through that structure like a liquid. This superionic state releases heat as it forms. If superionic water is actively forming inside Neptune today, it could be generating fresh thermal energy that adds to the internal heat output. The possibility of cryovolcanism sits at the edge of this discussion. On Neptune's moon Triton, the Voyager 2 spacecraft observed dark streaks on the surface consistent with geysers of liquid nitrogen shooting several miles into the sky. If a moon in Neptune's gravitational neighborhood can produce active cryovolcanism, it raises the question of whether the planet itself has something similar operating at much greater depth. A cryovolcanic plume inside Neptune's deep interior would not look like a lava flow. It would involve high-pressure mixtures of water, ammonia, and methane surging upward through fractures in the interior. The energy released by that surging fluid would heat the surrounding material. Over time, multiple such plumes could create the irregular interior density distribution that the gravitational data shows. This remains a theory, a serious one, supported by converging pieces of evidence, but without direct confirmation. Scientists cannot rule it out. And given everything else Neptune's interior appears to be doing, the idea of a geologically alive ice giant has moved from fringe speculation to a legitimate open question. The James Webb Space Telescope has been looking for specific signatures that would confirm or deny it. What it found in the South Polar region goes beyond any volcanic signal scientists were looking for. When the James Webb Space Telescope turned its instruments toward Neptune in 2022, scientists expected extraordinary detail. The telescope is the most powerful space observatory ever built. Its infrared instruments can detect heat signatures and chemical compositions with a precision that no previous telescope could approach. Researchers wanted to see Neptune's rings in fine detail, map its atmospheric chemistry, and study the faint heat patterns rising from its cloud tops. The ring images exceeded every expectation. The faint outer rings, barely visible to Hubble, appeared sharp and detailed in the Webb images. Dust arcs and structural details that had been theoretical became clearly visible. The atmospheric chemistry data came back rich with information about trace gases and layering. And then there was the glow. In the southern hemisphere of Neptune, the Webb telescope detected a faint but consistent emission of electromagnetic energy. The emission appeared across several infrared wavelengths and persisted across multiple observations taken on different dates. It was not an artifact. It was not a calibration error. The emission was real, coming from a defined region of the southern atmosphere, and it matched none of the signatures scientists had catalogued for known Neptune phenomena. To be precise about what this means, every source of light or heat emission from a planet falls into categories: solar reflection, thermal emission from warm gas layers, auroral glow caused by charged particles interacting with the magnetic field, chemical luminescence from specific atmospheric reactions. Scientists have a catalogue of what each of these looks like across different wavelengths. Each one has a fingerprint. The emission Webb detected from Neptune's southern hemisphere does not match any fingerprint in the catalogue. It is not solar reflection. The geometry is wrong for that. It is not the standard thermal emission pattern from warm gas. The spectral shape does not fit. It does not match Neptune's known auroral signatures, which are mapped to specific latitudes based on the position of the magnetic field. What remains when those known categories are eliminated is an unknown source. Several ideas have been put forward. One is that Neptune has a hidden radiation belt, a zone of high-energy charged particles trapped by the magnetic field at a position that has not been directly mapped. Radiation belts, like the Van Allen belts around Earth, emit specific kinds of energy as trapped particles interact with the planet's magnetic field. If a previously unknown radiation belt sits in the southern hemisphere, at the depth where Webb detected the emission, it could produce the signal. Another idea involves chemical luminescence from the upper atmosphere. Specific chemical reactions release light at specific wavelengths. If trace gases in Neptune's southern stratosphere are undergoing reactions driven by the planet's unusual internal chemistry, those reactions might produce a weak but consistent glow at infrared wavelengths. A third, more speculative idea links the emission to the volcanic hypothesis. If cryovolcanic activity deep inside the planet is pushing conductive material up toward the upper atmosphere in the southern hemisphere, that material could interact with Neptune's magnetic field and produce an unusual electromagnetic emission. None of these explanations have been confirmed. Researchers are collecting more Webb observations of the same region, hoping that additional data will narrow down the source. For now, Neptune is glowing in a way that science cannot yet explain, and right next to the glow, the telescope found something equally puzzling waiting in the rings. Every planet's atmosphere carries a chemical signature. The mix of gases present, the ratios between them, the trace compounds that appear in tiny quantities, all of it tells a story about the planet's history, its internal chemistry, and the processes running in its atmosphere right now. Scientists have detailed chemical profiles for every planet they have studied closely. Neptune's profile had been considered mostly complete based on Voyager 2 data and decades of subsequent telescope observations. The James Webb Space Telescope found things that were not supposed to be there. When Webb analyzed Neptune's atmospheric spectrum in high detail, it detected trace gases interacting in patterns that do not appear in any previous observation of an ice giant. The gases themselves are not new. They are known compounds found in various planetary atmospheres. What was unexpected was the way they were reacting with each other and with Neptune's primary atmospheric gases. Spectral analysis works by looking at which wavelengths of light a planet's atmosphere absorbs and emits. Each molecule has a unique absorption pattern, like a fingerprint. When Webb analyzed Neptune's near-infrared spectrum, certain absorption features appeared at wavelengths and intensities that did not match any standard model of Neptune's atmospheric chemistry. Some features suggested the presence of specific carbon compounds in greater concentrations than expected at the altitudes where they appeared. Other features pointed to nitrogen compounds showing up in chemical configurations that require specific pressure and temperature conditions to form. Those conditions do not match the known temperature and pressure at the altitudes where the compounds appeared. That mismatch is the problem. If a chemical compound appears at an altitude where the temperature and pressure should prevent its formation, something is transporting it from somewhere else. Either it is forming at a deeper, hotter, higher pressure level and being carried upward by vertical mixing, or it is being produced by a chemical reaction at high altitude that nobody has identified yet. The vertical mixing explanation connects to everything researchers have been finding about Neptune's dark spots and polar activity. If the planet's atmosphere is experiencing unusual upwelling from the deep interior, that upwelling would carry chemical material from high pressure depths up into the upper atmosphere. Compounds that form under extreme conditions deep in the troposphere could be detected at high altitudes where they would normally never exist. If that is what is happening, then Webb is essentially seeing the exhaust of Neptune's deep atmospheric engine. The chemical fingerprints riding upward on columns of rising gas are traces of processes happening far below where any telescope can directly observe. This matters beyond Neptune. Scientists use the chemical profiles of planets to build models of how planetary atmospheres evolve over billions of years. If ice giants can transport deep chemistry compounds to their upper atmospheres through unusual vertical mixing, then every chemical model built for ice giants on other star systems, and there are thousands of candidate ice giant planets discovered around other stars, needs to account for this process. Neptune may be teaching scientists how to read the atmospheres of worlds they will never be able to visit. Every unexpected compound Webb found is a data point that will reshape how researchers interpret the chemistry of planets across the galaxy. But while Webb was busy rewriting the rules of atmospheric chemistry, it was also capturing something above the atmosphere entirely. The rings around Neptune were telling their own impossible story. Every planet with rings eventually loses them. The rings around Saturn are slowly raining down into the planet's atmosphere. Scientists estimate Saturn could lose its iconic rings within 100 million years. The rings of Uranus are thin and sparse, already eroding. Ring systems spread out over time as the particles within them collide, drift, and gradually disperse. Physics guarantees it. Given enough time, a ring system either falls into the planet or spreads so thin it disappears. Neptune's rings are ignoring that guarantee. The planet has several faint rings circling it at different distances. Most of them are diffuse and unremarkable, spread into loose sheets of dust and ice particles that fade in and out of detection. But within the outermost ring, astronomers identified a set of dense, compact clumps. Scientists call these arcs. They are regions where the ring material packs together into thick, curved concentrations rather than spreading evenly around the orbit. These arcs were first spotted by Voyager 2 in 1989. Astronomers assumed they would dissolve quickly. Ring arcs are inherently unstable. The particles in an arc move at slightly different speeds depending on their exact distance from the planet. Particles on the inner edge of the arc move faster than those on the outer edge. That speed difference gradually pulls the arc apart, smearing its material around the full orbit within years or decades. By every standard model, Neptune's arcs should have been gone long before Voyager 2 arrived. They were not. And decades after Voyager 2's flyby, they are still there. The James Webb Space Telescope captured detailed infrared images of Neptune's ring system in 2022. And the arcs appeared clearly, dense and compact, maintaining their shape against the relentless mechanical pressure that should have destroyed them. The leading explanation involves shepherd moons. These are small moons orbiting close to a ring that use their gravitational pull to herd ring particles back into place. A moon orbiting just outside the arc would slow down particles that drift outward, while a moon just inside would push back particles drifting inward. Together, they would effectively trap the arc material in place. One moon has been identified near the arc region. Scientists have named it Galatea, and its orbit does appear to align in ways that could produce a trapping effect. Models have been built suggesting Galatea's gravitational resonance creates specific orbital zones where arc material tends to collect. The problem is that the models do not fully explain the arc's behavior. The arc structures shift in brightness and density over time in ways that Galatea alone cannot account for. Some arcs have faded while others have brightened. The material inside them appears to be redistributing itself in patterns that no current Shepherd moon simulation can reproduce. Scientists suspect there may be additional small moons buried within or near the arcs that have not yet been detected. Objects as small as a mile across could have significant gravitational influence on ring particles at close range, yet would be essentially invisible to current telescopes at Neptune's distance. The Webb images gave researchers the most detailed view of the arc structure ever captured. What they revealed was a level of internal organization that made the mystery deeper. The arcs contain fine-scale structure, brightness variations at small scales suggesting concentrated pockets of denser material embedded within them. Something is organizing Neptune's ring arcs from the inside, and whatever it is it has been doing so since before humanity discovered the planet. Neptune has 14 confirmed moons. The largest is Triton, a world so strange it deserves its own investigation. The rest range from medium-sized to small, most of them discovered relatively recently as telescope technology improved. The outermost ones orbit in chaotic, tilted paths that suggest Neptune captured them from the surrounding region rather than forming them alongside the planet. But the ring arc mystery points to the possible existence of moons that have never been seen. To keep ring arcs stable for decades, the gravitational influence needed is precise and constant. Galatea produces some of it. The remaining instability in the arc patterns suggests additional sources of gravitational shepherding. Objects small enough to avoid detection in current telescope surveys, yet large enough to exert meaningful pull on ring particles, could be hiding in the ring plane itself. Finding a moon less than a mile across at a distance of nearly 3 billion miles is genuinely beyond current observational capability. Even the Hubble Space Telescope and the James Webb Space Telescope, the two most powerful space observatories ever operated, have resolution limits that make objects of that size invisible at Neptune's distance. Researchers have searched the ring system images systematically, looking for any brightness fluctuation that might indicate a small embedded object. They have built detection algorithms designed to identify the faint gravitational shadows that a small moon would cast on nearby ring particles. Each search has come up empty. That absence of detection does not prove the moons are absent. It proves only that current instruments cannot confirm them. Scientists working on ring dynamics models routinely include the possibility of undetected embedded moons as a free variable in their simulations. When they do, the models fit the observed arc behavior better than when they leave those objects out. The implication is striking. Neptune may host an entire population of small moons, objects that have been orbiting the planet since the solar system formed, and we have no direct evidence of their existence. Their presence is inferred from the behavior of dust. This situation is not unique to Neptune. Planetary scientists suspect that embedded ring moons are common around planets with complex ring structures. Saturn's rings contain several confirmed embedded moonlets discovered by the Cassini spacecraft during its close orbital mission. Cassini spent 13 years orbiting Saturn and could detect objects as small as half a mile across within the rings. A similar mission around Neptune could potentially reveal an entirely unknown family of small moons. The absence of that mission is its own story, and one worth coming back to. But the invisible moon problem also connects to a larger question about Neptune's entire satellite system. Because the one moon that scientists can see clearly, Triton, is itself one of the most bizarre objects in the solar system. A world that travels backward around Neptune at a steep angle covered in geysers, almost certainly captured from somewhere else entirely. Triton did not form here. Something brought it into Neptune's orbit, and the forces required to do that would have been catastrophic for anything that was already orbiting the planet before Triton arrived. The scale of that catastrophe is worth sitting with. A moon roughly 1,700 miles wide, captured from the outer solar system, would have been moving at enormous speed when it first entered Neptune's gravitational sphere. The energy involved in slowing it down and pulling it into a stable orbit would have radiated through the entire system. Original moons would have been scattered, orbital debris would have rained inward for millions of years. Out beyond Neptune, past the orbits of the known dwarf planets, the solar system does not simply end. It continues outward in a vast, dark region filled with icy objects left over from the solar system's formation. This region is called the Kuiper Belt, and Neptune's gravity shapes everything inside it. In 2025, astronomers confirmed the existence of a distant rocky body in an orbital configuration that stopped the planetary science community cold. The object, discovered through careful analysis of telescope data, orbits the Sun in a path that locks it into a precise gravitational relationship with Neptune. For every 10 complete orbits Neptune completes around the Sun, this object completes exactly one. One orbit for the object. 10 for Neptune. A 10-to-1 rhythm maintained with a precision that pure chance cannot explain. This kind of gravitational locking is called orbital resonance. It happens when two objects interact gravitationally in a way that keeps their orbital periods in a stable ratio. The ratio 1 to 10 is among the most extreme resonances ever confirmed for a solar system body. Neptune already has a well-documented history of capturing objects into resonance. Pluto is locked in a 2 to 3 resonance with Neptune, completing 2 orbits for every 3 Neptune completes. A large population of other Kuiper Belt objects sit in similar resonances at simpler ratios. Neptune's gravitational reach is long and powerful enough to sculpt the distribution of objects in the outer solar system across billions of years. A 1 to 10 resonance is different. Simple resonances like 2 to 3 arise naturally over time as objects drift and exchange energy with Neptune. An extreme resonance like 1 to 10 is much harder to establish. The gravitational mechanics required to pull an object into that specific rhythm and keep it there point to something unusual in the history of the outer solar system. The most plausible explanation involves a violent early period in the solar system when the giant planets were migrating outward from their original formation positions. As Jupiter, Saturn, Uranus, and Neptune shifted outward over millions of years, their gravitational influence swept through the outer solar system like a cosmic plow, flinging objects outward, capturing some into resonances and ejecting others entirely. A 1 to 10 resonance object would have required an extreme version of that process. The object would need to have been placed in a very specific orbit, with a very specific energy, at the right moment during Neptune's migration, for the resonance to lock in and hold. Even small variations in the initial conditions would have broken the resonance before it stabilized. The fact that this object exists and is still in that resonance today suggests the early solar system was even more chaotic and violent than current migration models predict. Neptune's reach extended further and hit harder than the standard picture assumes, and if the outer solar system was more violently rearranged than scientists thought, then the current positions of objects in the Kuiper Belt, and what they might imply about even more distant objects, deserve a second look. Scientists have been mapping the Kuiper Belt for decades. As the catalogue of objects grows, the patterns in their orbital distribution keep surprising researchers. Objects that should be randomly scattered instead cluster in specific resonances, at specific angles. Neptune's fingerprints are everywhere. But some of the patterns cannot be explained by Neptune alone, suggesting the early solar system was even more crowded and violent than any model yet captures. The 1 to 10 resonance object is only the most recently confirmed data point in a picture that keeps growing more complicated. Neptune was not always at its current address. The planets of the outer solar system formed closer to the Sun than they orbit today. In the early history of the solar system, roughly 4 billion years ago, all 4 giant planets occupied a more compact region. Then, something destabilized the arrangement. Gravitational interactions between the giants began pushing them outward. Jupiter moved slightly inward. Saturn, Uranus, and Neptune all shifted outward, migrating to their current orbital positions over millions of years. This migration period, which scientists call the Nice model, after the city in France, where researchers first developed the framework, is now accepted as a key chapter in the solar system's history. But the evidence coming from Neptune's gravitational influence on the outer solar system is forcing a revision of that chapter. The standard Nice model predicts a specific distribution of objects in the Kuiper Belt based on how violently Neptune migrated and how far it moved. Comparing those predictions to actual observations of the Kuiper Belt has produced repeated mismatches. The real distribution of objects out there is more extreme than the model predicts. There are more objects in unusual orbits, more extreme resonances, and more distant scattered bodies than a smooth migration scenario can account for. The 1 to 10 resonance object is one data point in that mismatch. There are others. A group of distant Kuiper Belt objects orbits in a clustered pattern that some researchers argue points to gravitational shepherding by a large, undiscovered planet far beyond Neptune. This hypothetical world, sometimes called Planet 9, would need to be several times Earth's size to produce the observed clustering. Planet 9 has not been confirmed. The clustering could have other explanations, including random chance or selection bias in how astronomers search the sky, but the clustering is real data, and Neptune's known gravitational influence alone cannot produce it. What this means for Neptune is important. If the outer solar system contains structures that Neptune's current orbit and mass cannot explain, then either the models of Neptune's migration are wrong, or there is additional mass out there that science has not yet catalogued. Either possibility changes how researchers think about Neptune's role in the solar system. The planet is not simply orbiting at the edge and quietly shaping the Kuiper Belt. It may have undergone a more dramatic migration than currently modelled, leaving behind a pattern of gravitational signatures that researchers are still mapping today. And Neptune's influence on the outer solar system connects back to the planet's interior. A more violent migration would have involved gravitational interactions that could have heated Neptune's interior, or disturbed its core structure. The irregular interior density distribution that gravitational measurements reveal today could partly be a scar left by those ancient collisions and interactions. The outer solar system is a crime scene with evidence pointing in every direction. Neptune is at the center of it. And the next piece of evidence comes from a feature of the planet so fundamental, so built into its identity, that scientists assumed they understood it completely. Neptune's orbital migration during the early solar system was energetic enough to scatter objects billions of miles from their original positions, lock others into extreme resonances, and leave behind a Kuiper Belt structured in ways that still generate scientific debate. Every ring arc, every captured moon, every resonant object is a scar from that period, and the planet itself carries scars on the inside. The colour. It turns out they did not fully understand even that. Neptune is blue, spectacularly, vividly blue. In Voyager 2's images, the planet glows with a deep, rich colour that looks almost artificial. Photos of Neptune have been used in textbooks, posters, and science articles for decades as the defining visual of a distant ice giant. That blue is one of the most instantly recognizable sights in solar system photography. The explanation seemed simple. Methane gas in Neptune's atmosphere absorbs red light and reflects blue light back into space. The more methane, the deeper the blue. Uranus has methane too, and it appears blue-green. Neptune appears deeper blue. Scientists attributed the difference to Neptune's slightly higher methane concentration. Then researchers started comparing Uranus and Neptune more carefully. The two planets have nearly identical atmospheric compositions when measured by spectroscopy. Methane concentrations in their upper atmospheres are remarkably similar, close enough that methane alone cannot account for Neptune's much deeper, more saturated blue colour. Something else is producing the visual difference. A team of atmospheric scientists analysing both planets in detail proposed that a photochemical haze sits above the methane layer in both atmospheres. This haze forms when sunlight, specifically ultraviolet light, breaks apart methane molecules and causes the fragments to reassemble into larger, more complex molecules. Those molecules form tiny particles that gather into a haze layer sitting high in the atmosphere. On Uranus, this haze appears to be thicker and more uniform. A denser haze scatters more light and makes the planet appear lighter in colour. On Neptune, the haze layer appears to have a different structure, possibly because the atmospheric dynamics on Neptune are more active. Neptune's stronger internal heat drives more vertical mixing. which may continuously disrupt and refresh the haze layer in ways that keep it thinner and more patchy. A thinner haze on Neptune lets the methane blue color dominate more strongly. The result is the deep, saturated blue visible in images. If this model is correct, it means Neptune's striking appearance is a direct symptom of its mysterious internal heat. The beautiful blue color is the visual signature of an active planetary interior. But even this explanation leaves room for uncertainty. The haze model is supported by the data, and scientists are fairly confident in its broad strokes. The specific mechanisms controlling how internal dynamics affect haze thickness are still being worked out. Small changes in how the haze forms could produce noticeable color shifts on timescales of years, which raises an interesting possibility. If Neptune's internal heat output is irregular, as the temperature data suggests, then the haze thickness could vary over time as the atmospheric mixing intensity changes. A period of stronger internal heat output would produce more vigorous mixing, thinner haze, and deeper blue. A quieter interior period would produce a thicker haze and a paler, more washed-out color. Astronomers who have compared Neptune images across decades have noticed subtle color variations. The planet does appear to shift slightly in shade over time. Whether those shifts track the internal heat cycle, the solar cycle, or some combination of both is an open investigation. Neptune's color is not just a pretty fact. Every shade it wears is a measurement of something happening deep inside. The color is also a reminder of how much scientists inferred about this planet before they truly understood it. For decades, Neptune's blue was filed as a simple fact of atmospheric chemistry. Now it is evidence in an ongoing investigation. Every visual detail of the planet, down to its shade of blue, has turned out to carry information about processes nobody expected to find. Uranus and Neptune formed in the same region of the early solar system. They have similar masses, similar sizes, similar atmospheric compositions, and similar structures. Scientists group them together as the ice giant class of planets, a category distinct from the gas giants Jupiter and Saturn, and from the rocky terrestrial planets like Earth and Mars. By every broad measure, these two planets should behave in similar ways. They do not. Uranus is geologically quiet. Its internal heat output is negligible. The planet radiates back almost exactly the same amount of energy it receives from the Sun, suggesting its interior has cooled to near equilibrium over the age of the solar system. Its atmosphere is calm by comparison. Wind speeds on Uranus are fast by Earth standards, but far below what Neptune generates. Its weather systems are subdued. Neptune generates more than twice as much energy as it receives from the Sun. Its winds are the fastest in the solar system. Its atmosphere cycles through violent storms, temperature anomalies, and cloud disappearances. Its interior is clearly doing something active. Two planets of the same class, formed in the same region, diverging dramatically in their internal energy output. Scientists have been trying to explain this gap for decades. One proposal involves the history of each planet's collisions. In the chaotic early solar system, giant impacts between large rocky and icy bodies were common. The leading hypothesis for why Uranus is tilted almost completely on its side, with its poles pointing nearly at the Sun, is that a massive object struck the planet long ago and knocked it over. If a giant impact struck Uranus at an angle that disrupted its interior mixing, it could have created a thermal barrier layer deep inside the planet. Heat generated in the core would become trapped below that barrier, unable to escape upward into the atmosphere. The planet would appear externally cool while sitting on a reservoir of internal heat that slowly bleeds out over billions of years. Neptune may have escaped that kind of disruptive collision, allowing its interior to continue mixing heat upward normally. Or Neptune may have experienced a different kind of impact that had the opposite effect, triggering more vigorous interior convection rather than shutting it down. These ideas are plausible frameworks, direct confirmation is impossible without sending probe missions into each planet's interior, something no current technology can do. The divergence between Uranus and Neptune matters beyond just these two planets. Ice giants are now believed to be the most common type of planet in the galaxy. Surveys of exoplanets, planets orbiting other stars, consistently show that planets between Earth's size and Neptune's size are incredibly abundant. Understanding why two ice giants right here in our solar system can develop such different internal behaviors is a foundational question for understanding planetary evolution across the universe. The answer might be written in Neptune's excess heat, and tracing that heat to its source points directly back to the interior, where the next mystery has been quietly building for years. The Uranus-Neptune divergence also highlights a problem with how scientists classify exoplanets. When a planet is detected around another star and its size falls between Earth and Neptune, researchers call it a sub-Neptune or a mini-Neptune and apply models built from observing these two planets. But if Uranus and Neptune, both right here in our own solar system, follow such different internal rules, applying a single model to distant worlds of similar size becomes much less reliable. Earth has radiation belts. They are zones of high-energy charged particles trapped by the planet's magnetic field, circling Earth in two donut-shaped regions above the atmosphere. Named after the scientist who discovered them, these belts were found in 1958 by one of the first American satellites. They carry particles that can damage spacecraft electronics and pose serious radiation hazards to astronauts passing through them. Every planet with a magnetic field can potentially have radiation belts. Jupiter has the most powerful in the solar system, so intense that spacecraft flying through them receive damaging radiation doses in minutes. Saturn has belts. Even Mercury has a weak set detected by an orbiting spacecraft. Neptune has a magnetic field, a powerful and strange one, tilted and off-center. Scientists expected radiation belts to come with it. Voyager 2, during its 1989 flyby, detected evidence of charged particles trapped in Neptune's magnetic field. The measurements suggested a radiation belt exists, but the flyby was brief. Voyager 2 crossed Neptune's magnetic field environment in a matter of hours, and then kept moving, never to return. The measurements it made were snapshots, not the detailed mapping that a dedicated orbiter would produce. Scientists built rough models of Neptune's radiation belts based on those snapshots. The models suggested a modest radiation environment, less intense than Jupiter's but significant. For 3 decades, those models went largely unchallenged because no new data arrived to challenge them. The James Webb Space Telescope's observations complicated the picture. The glow detected in Neptune's southern hemisphere, the one with no confirmed source, fits several potential explanations. One of the more serious proposals is that it represents auroral or radiation belt emission from a region of the magnetic field that Voyager 2's brief flyby missed entirely. Neptune's magnetic field is so tilted and off-center that it creates a highly unusual trapped particle environment. Unlike Earth's symmetric radiation belts, Neptune's belts would follow the asymmetric field geometry, creating zones of concentrated radiation at unexpected latitudes. The southern hemisphere, where Webb detected the anomalous glow, corresponds to a region where an asymmetric radiation belt could concentrate high-energy particles in a way that Voyager 2's trajectory simply never sampled. If a hidden or poorly mapped radiation belt exists in Neptune's southern magnetic field region, it would emit radiation at specific wavelengths as trapped particles interact with the local magnetic environment. Some of those emissions would fall in the infrared range that Webb is sensitive to. This remains a hypothesis. Scientists cannot rule it in or out with existing data. Confirming it would require a spacecraft orbiting Neptune for months or years, sampling the magnetic field environment at different latitudes and longitudes, building a complete three-dimensional map of the trapped particle populations. No such mission exists. The gap in knowledge is real and acknowledged. And sitting right next to the radiation belt question, connected through the same deep southern atmospheric region, is a possibility that planetary scientists have been reluctant to say out loud. The absence of a Neptune orbiter means scientists are trying to diagnose the radiation belt from 3 billion miles away using telescopes designed for different purposes. If a hidden radiation belt is producing the southern glow, researchers may not be able to confirm it without a dedicated magnetometer and particle detector in orbit around the planet. The James Webb Space Telescope, powerful as it is, captures light. It cannot measure particle populations or map field geometries the way a spacecraft flying through them would. Every instrument ever sent to Neptune crossed its environment in hours. A complete picture would require months or years of orbital measurement. Cryovolcanism sounds like something from a science fiction story. Cold volcanoes. Eruptions of frozen material instead of molten rock. The concept is real. Several bodies in the outer solar system have demonstrated active cryovolcanism. Neptune's moon Triton produces dark geysers that shoot liquid nitrogen several miles into the sky. Saturn's moon Enceladus fires jets of water vapor and ice particles from cracks near its south pole. Europa, one of Jupiter's moons, is suspected of having similar activity beneath its ice shell. These examples share a common driver: tidal heating. As a moon orbits its planet, the planet's gravity flexes the moon's interior in a rhythmic squeeze, generating friction and heat. That internal heat melts material and drives eruptions. Neptune is a planet, not a moon. Tidal heating from an outside body does not apply in the same way. So what would drive cryovolcanic activity inside Neptune itself? The answer potentially lies in the same processes that explain the planet's excess internal heat output. If material deep inside Neptune is undergoing phase transitions, specifically if water and ammonia under extreme pressure are transitioning into the superionic state discussed in relation to the planet's magnetic field, those transitions release energy. Phase transitions involving large amounts of material over long timescales could generate a significant heat flow. That heat has to go somewhere. In a planet with an irregular interior, where dense pockets of material are distributed unevenly throughout the core region, heat would not flow outward uniformly. It would concentrate in some regions and find paths of least resistance to escape upward. In regions where that upward heat flow is especially concentrated, the combination of heat and pressurized fluid material could produce plume-like eruptions into the layers above. These would look nothing like Earth volcanoes. Deep inside Neptune, at pressures thousands of times greater than anything on Earth's surface, the material involved would be a superhot mixture of water, ammonia, and methane under extreme compression. The eruptions would not break through to the visible atmosphere. They would push material upward through the interior layers, redistributing heat and chemistry in ways that would eventually show up in atmospheric measurements. The irregular core density distribution found in gravitational data is consistent with this picture. Uneven dense pockets could be the remnants of where cryovolcanic plumes have concentrated heavier material over billions of years of activity. The South Pole temperature spike fits too. A cryovolcanic plume active below the southern hemisphere would push a concentrated column of heat upward through the interior toward the southern surface, producing exactly the kind of localized. Rapid temperature increased that thermal imaging recorded between 2018 and 2020. None of this is confirmed. Scientists are careful to label the cryovolcanic hypothesis as speculative, but serious. The convergence of the gravitational anomaly, the excess heat, the polar spike, and the unidentified southern glow all point in the same direction. The question is whether that direction leads to cryovolcanism or to something else entirely that nobody has yet classified. Scientists are also aware that ruling out cryovolcanism from 3 billion miles away is nearly impossible with current instruments. A weak cryovolcanic plume deep in Neptune's interior would leave atmospheric and thermal traces that could be mistaken for other processes, or could be too faint to detect at all from Earth orbit. The same limitations that prevent confirming it prevent ruling it out. What researchers can say with confidence is that the interior of Neptune is doing something energetically significant, and that the phenomenon driving it has not yet been given a name that fits all the evidence. Of all the mysteries attached to Neptune, Triton is the one that comes with the most dramatic backstory. Triton is Neptune's largest moon, roughly 1,700 miles across, and it orbits the planet in a direction opposite to Neptune's rotation. Every other large moon in the solar system orbits in the same direction as its planet rotates. This is a direct consequence of how moons form. They coalesce from the same disk of material that forms the planet, spinning in the same direction as everything else in that disk. A moon in a retrograde orbit, going the wrong way, did not form from that disk. It was captured. Triton almost certainly originated in the Kuiper Belt. Before Neptune captured it, Triton was likely a large Kuiper Belt object drifting through the outer solar system. At some point, gravitational dynamics brought it into Neptune's vicinity, and the encounter that followed resulted in Triton being pulled into orbit around the planet. That capture event would have been catastrophic for any moons that were already orbiting Neptune at the time. A large object entering the Neptune system from outside would disrupt existing orbits through close gravitational encounters. Some of Neptune's original moons may have been flung out of the system entirely. Others may have had their orbits scrambled into the chaotic tilted paths that Neptune's outer irregular moons follow today. And Triton's retrograde orbit is slowly decaying. Every orbit, the moon loses a tiny amount of energy to tidal interactions with Neptune. Over time, that energy loss is bringing Triton closer to the planet. Scientists calculate that in roughly 350 million years, Triton will fall inside a boundary called the Roche limit, where tidal forces will tear the moon apart. The debris will form a ring system around Neptune, far more spectacular than the current faint arcs. Neptune will eventually wear its largest moon as a ring. Triton also has surface features that Voyager 2 imaged during the 1989 flyby. Dark streaks on the surface pointed to active geyser activity. The geysers appear to shoot material several miles into the thin atmosphere. The energy source for this activity, on a moon so far from the sun, was debated for years. The current understanding is that sunlight, even at Neptune's distance, is enough to heat nitrogen ice just below Triton's surface. The warmed nitrogen turns to gas, builds pressure, and erupts through the icy crust in jet like plumes. A captured Kuiper Belt object, producing active geysers, in a retrograde decay orbit around a planet full of its own mysteries. Triton raises a question that has no clean answer. How many other large captured objects are hiding in the outer solar system, and what happens to a planetary system every time one gets pulled in? The next piece of this puzzle sits even further from Neptune than Triton, out in the deep dark where the planet's gravity still reaches. Triton also represents a scientific opportunity that will not last forever. The moon is geologically active today. Its geysers are firing. Its surface is young enough to still show fresh deposits from recent eruptions. But Triton is falling. Every orbit brings it slightly closer. In geological time, the window to study an active Triton before tidal forces begin to tear it apart is closing. A spacecraft arriving at Neptune in the 2040s would find Triton still active. A mission delayed by another century might find a moon already beginning to fracture at its margins. When the James Webb Space Telescope turned its infrared detectors toward Neptune in 2022, the scientific team was expecting to see rings. They had already been visible in Hubble images, The basic structure of Neptune's ring system, several faint bands at different distances from the planet, with a set of dense arcs in the outermost ring, had been documented over decades. Webb's job was to provide a sharper picture. What came back exceeded every expectation. The rings appeared in the Webb images with a clarity and detail that no previous telescope had achieved. The arcs in the outer ring were well defined, their shapes and internal brightness variations visible in ways that past observations had only hinted at. The fainter inner rings, barely detectable in Hubble imagery, resolved into distinct bands with measurable structure. But the detail revealed something puzzling. The arcs are not smooth. Within each arc, the material is organized into smaller clumps and voids, alternating concentrations of denser and less dense ring particles. The clumping happens at scales much smaller than can be explained by the gravitational shepherding of Galatea alone. If Galatea's resonance creates the large-scale arc structure, something else is creating the fine-scale clumping inside each arc. One proposal suggests that collisions between ring particles themselves are responsible. When particles within an arc collide at low speeds, they can clump together rather than shattering. Over time, those clumps could grow by accreting additional particles, creating the small dense knots that Webb detected. If this process is ongoing, the arcs may be in the early stages of building very small moonlets inside themselves. That would be a remarkable observation. Ring particles spontaneously organizing into proto-moons through self-gravity and low-speed collisions is a process that planetary scientists believe shaped the formation of the solar system itself. Watching it happen in a ring system today would be like watching the solar system's earliest days in miniature. The Webb images also revealed that the arcs are changing. Comparing the 2022 images to earlier Hubble observations showed shifts in the relative brightness of different arc segments. One arc that appeared brighter in earlier observations had faded noticeably. Another had intensified. The material inside the arcs is moving around in ways that the Shepherd Moon model alone cannot account for. Every image Webb sends back from Neptune raises as many questions as it answers. The rings that were supposed to be a straightforward part of the planetary inventory are showing dynamic behavior that keeps surprising researchers. And the planet's behavior overall has begun to push scientists toward a question that applies well beyond Neptune. If one of the 8 planets in our solar system can defy models this dramatically and consistently, what does that say about every planet model ever built? The Webb images also changed how researchers think about ring dynamics more broadly. For decades, ring science was dominated by Cassini's observations of Saturn's ring system. Saturn's rings are bright, dense, and close enough to study in extraordinary detail. Neptune's rings are faint, distant, and structurally very different. The detailed Webb images of Neptune's ring arcs provide a second complete case study of a ring system behaving in unexpected ways. The fact that both Saturn and Neptune produce ring anomalies that defy simple models suggests that ring systems across the solar system and around planets in other star systems are routinely more complex and dynamic than theoretical models predict. The ring science alone justifies a dedicated Neptune mission. Every year of Webb observation adds new detail to the arc structure, but each new detail deepens the puzzle rather than resolving it. A single anomalous reading from a distant planet can be filed away as instrument error or a one-time event. 2 anomalies invite a second look. 3 or 4 begin to look like a pattern. But when the anomalies keep arriving, every few years, from different instruments, different observatories, and different research teams all studying the same planet, the pattern becomes impossible to dismiss. Neptune has been accumulating anomalies for decades, and the rate at which new, unexplained behavior appears to be increasing. In the 1990s, the anomalies were the vanishing Great Dark Spot and the appearance of replacement storms in unexpected locations. In the 2000s, The 15-year stratospheric cooling trend began quietly and went largely unexplained. In the late 2010s, the South Pole heated up and the entire cloud layer disappeared. In the early 2020s, Hubble documented the storm reversal, and the James Webb Space Telescope found the unclassified southern glow, the trace gas anomalies, and the unexpected ring arc structure. Each era of observation produces a new layer of strangeness. The strangeness does not repeat. Each discovery is different from the ones that came before, adding to the total rather than explaining what was already there. Researchers who have spent careers studying Neptune have noted this pattern with increasing unease. If the anomalies were random events with no connection to each other, the rate of new discoveries would be driven primarily by improvements in telescope technology. Better instruments see more, so finding new things is expected. But some of what has been discovered in recent years would have been detectable by older instruments if it had been present earlier. The South Pole temperature spike, for example, could have been detected by the same infrared instruments available in the 1990s. The stratospheric cooling trend was measurable from the early 2000s onward. These are not new phenomena revealed by better optics. They are phenomena that started during the observation period. That raises the possibility that Neptune's behavior is genuinely changing over time. Something about the planet's internal or atmospheric dynamics may be intensifying, producing new and stronger anomalies as the underlying processes evolve. What could drive that kind of escalation? If Neptune's interior contains an ongoing process, whether phase transitions, deep circulation, or something unclassified, that process could be progressing through different stages. An interior that was in a stable, slow state a century ago might be entering a more active phase today. The thermal data, the magnetic field, and the atmospheric chaos could all be symptoms of an interior that is shifting from one state to another. Scientists are careful not to overstate this. The dataset is still limited. Neptune has been studied in detail for a relatively short period of astronomical time. What looks like escalation over 50 years of observation might be normal variation on a timescale of centuries, but the possibility that researchers are watching Neptune change in real time is enough to make the case for a dedicated mission more urgent than ever. Because the window to understand what is happening now, while it is happening, may be shorter than anyone assumed. The storm that reversed in 2020, the glow detected by Webb in 2022, the ring arc changes between telescope sessions, all of these are in motion right now. What an orbiter arriving in the 2040s might find could be storms in new configurations, a faded or strengthened southern glow, and ring arcs rearranged further still. The observations made today from Earth establish the baseline for that future measurement. Every limitation in our understanding of Neptune comes back to one fundamental fact. Neptune is 2.8 billion miles from Earth. That distance shapes everything about how scientists study the planet, and it creates problems that no telescope can fully solve. Light travel time alone is a significant challenge. When a telescope points at Neptune and captures an image, the light in that image left the planet roughly 4 hours earlier. A storm event observed today actually happened 4 hours ago, in a fast-moving atmosphere where storms can shift and change direction in hours. That delay means scientists are always watching the recent past rather than the present. Two-way communication with a spacecraft at Neptune would take over 8 hours. A probe orbiting Neptune could send a message asking for instructions, and the reply would arrive more than 8 hours later. Autonomous operation would be essential. Any spacecraft operating there would need to handle complex situations without waiting for human direction. The angular size of Neptune in the sky is also a fundamental barrier. At its distance, Neptune appears as a tiny disk. Even in the most powerful telescopes, atmospheric features smaller than roughly 1,000 miles across are difficult to resolve clearly. Many of the processes scientists believe are driving Neptune's behavior, the deep circulation, the interior mixing, the small-scale chemistry, happen at scales that current technology cannot observe from Earth. The Hubble Space Telescope has a mirror 2.4 meters wide. The James Webb Space Telescope has a mirror 6.5 meters wide. Both represent the frontier of what has been launched into space. Both struggle to resolve the fine detail that would answer the most pressing Neptune questions. A spacecraft orbiting Neptune at close range, something equivalent to what Cassini did at Saturn or Juno is doing at Jupiter, would transform the science. At orbital distances, a probe could resolve atmospheric features just a few miles across, map the magnetic field in 3 dimensions, sample the atmospheric chemistry directly, and track individual storm systems over months, rather than catching brief glimpses between telescope sessions. The distance also means the mission would take a long time to arrive. Using current propulsion technology, a Neptune orbiter mission would take roughly 15 to 16 years of travel time after launch. A mission approved today would not arrive until the early 2040s. The data from that mission would begin returning in the mid-2040s. This is why planetary scientists describe Neptune as simultaneously the highest priority target in the outer solar system and the least resourced. The science case is enormous. The practical barriers are real. And while the discussion about a future mission continues, every year that passes without one is another year of anomalies accumulating without explanation. The good news is that every anomaly accumulating now will be waiting when a mission finally arrives. Neptune is storing its secrets for investigators, but the urgency is growing, because the more scientists look at what Neptune is doing, the more they realize the implications extend far beyond this one planet. Neptune is the anchor point for our understanding of ice giant physics. Every model of sub-Neptune and mini-Neptune exoplanets, the most common type of planet in the galaxy, rests partly on assumptions derived from studying the 2 ice giants right here. If Neptune is breaking those assumptions across every major system simultaneously, the models applied to thousands of exoplanets are carrying the same errors. The urgency of understanding Neptune is proportional to the number of worlds whose characterization depends on getting Neptune right, and that number is in the thousands. Planetary science builds on analogy. When researchers study a new planet, they apply frameworks built from studying planets they already understand. The models developed from studying Earth inform how scientists interpret Mars. The lessons from Jupiter shaped expectations for every gas giant discovered around another star. The assumptions about ice giant behavior, built from early observations of Uranus and Neptune, have been applied to thousands of candidate ice giant planets identified in other star systems. Neptune is dismantling several of those assumptions simultaneously. The assumption that an ice giant's atmospheric activity scales with its proximity to its star has been contradicted by Neptune's excess internal heat and violent weather. The assumption that ice giant interiors are geologically passive contradicts the gravitational data pointing toward an irregular, possibly active interior. The assumption that ice giant magnetic fields are roughly symmetric and centered near the core has been contradicted by Neptune's tilted, off-center field. Each contradiction in the Neptune data represents a flaw in the model, and that flaw applies not just to Neptune, but to every planet classified using the same model. Researchers studying distant exoplanets do so almost entirely through indirect measurements. They measure how much light a planet blocks as it passes in front of its star. They analyze the wobble the planet induces in its star's motion. From these signals, they can infer mass, size, approximate composition, and orbital parameters. They cannot directly image most of these planets in any detail. To interpret those indirect measurements, scientists rely on models of planetary structure and behavior. Those models are calibrated against the planets they can study directly. If Neptune's interior behavior, magnetic field, and atmospheric dynamics do not match current models, then the models used to interpret distant ice giant observations are wrong in the same ways. A planet in another star system that looks like Neptune from its transit signal might have a completely different internal activity level, a completely different magnetic field geometry, and a completely different atmospheric chemistry than any model currently predicts. Scientists would have no way to know, because the model they would use to interpret the signal was built on flawed assumptions about Neptune. Correcting those assumptions requires understanding Neptune, and understanding Neptune requires the kind of up-close, extended observation that only a dedicated orbital mission can provide. The stakes extend beyond academic interest. Identifying which distant planets might have conditions relevant to habitability, whether they retain atmospheres, whether they have active interiors that could drive surface chemistry, requires accurate models of how planetary interiors and atmospheres behave. Neptune is breaking those models right now. Fixing them could change which worlds scientists prioritize as targets for future study. One planet's anomalies are rewriting the handbook for how to read an entire class of worlds, and the question driving every researcher who works on Neptune today is the one that every piece of evidence points toward, but none of them can yet answer. Sub-Neptune and mini-Neptune planets have been discovered in the thousands since the launch of the Kepler Space Telescope. They are the dominant planetary type in survey data. For every planet like Earth or Jupiter that astronomers detect, they find several in the Neptune-sized range. Classification of these worlds as likely habitable, likely rocky, likely volatile rich, or likely gaseous relies on mass and radius measurements interpreted through models calibrated on Uranus and Neptune. Models that Neptune is currently demonstrating are incomplete in fundamental ways. The correction of those models begins with understanding why Neptune behaves the way it does. Scientists have wanted to send a dedicated spacecraft to orbit Neptune for decades. The scientific case has been made repeatedly. A Neptune orbiter with an atmospheric probe would answer questions that no Earth-based or space telescope can approach. It would map the magnetic field completely, profile the atmospheric chemistry at multiple altitudes, track storm systems across full planetary cycles, and provide the close-range data needed to test every hypothesis that has been built up from a distance. In 2022, a major review of planetary science priorities recommended a Neptune orbiter and atmospheric probe as one of the highest priority large missions for the coming decade. The review, which represents the consensus of the planetary science community, ranked a Neptune mission above most other proposed outer solar system missions, specifically because of the scientific gaps that Neptune represents. The path from priority recommendation to approved mission is long. Funding must be secured, engineering studies must be completed, a spacecraft must be designed, built, and tested, and then it must travel for roughly 16 years to reach its destination. There is also a launch window consideration. Neptune orbiter missions benefit from using gravitational assists from other planets to accelerate the spacecraft and reduce travel time. The optimal trajectory options repeat on timescales of years. Missing a window means waiting years for the next opportunity. The scientific community has identified several potential trajectory options in the late 2020s and early 2030s. A launch in that window, using Jupiter for a gravitational assist, could reduce travel time significantly compared to a direct trajectory. If a mission launches in the early 2030s, it could arrive at Neptune in the mid-2040s. Scientists working on Neptune today are fully aware that a mission approved now would produce close-range data after many of them have retired. They are doing the groundwork for an investigation that a future generation will carry out. This is how planetary science has always worked. The scientists who designed Voyager 2 did not live to see all its results. The teams who built Cassini spent careers that overlapped only partially with the mission's operational life. The investment spans generations. What makes Neptune different from past targets is the accumulation of anomalies discovered entirely from Earth. Every other major outer solar system target, Jupiter, Saturn, Uranus, was visited by spacecraft before the depth of its strangeness was understood. Neptune has been revealing its strangeness from a distance, across decades of ground-based and space telescope observation, while the mission to investigate it remains unbuilt. The planet is essentially calling out to be investigated. Every anomaly is a question without an answer. Every unexplained glow, every reverse storm, every vanishing cloud layer is a data point waiting for the up-close follow-up that only an orbiting spacecraft can provide. And the answer to all of it, whatever it turns out to be, may require scientists to add a category to their understanding of how planets work. A Neptune orbiter would also carry instruments designed to probe the atmosphere directly, releasing a probe that descends into the cloud layers and transmits data until the pressure crushes it. That probe, dropping through the visible clouds and into the deeper atmospheric layers, would measure temperature, pressure, and chemistry in real time at depths never sampled. The composition data alone would settle several open questions about the source of Neptune's excess heat and the origin of the trace gas anomalies. Scientists have planned the instrument packages, the engineering concepts exist. What is needed is the commitment to build and launch the mission. Planetary science operates on rules. Rules about how atmospheres retain heat. Rules about how magnetic fields form. Rules about how ice giants cool and quiet over billions of years. Rules about how ring systems behave. Rules about how orbital resonances develop. These rules were built carefully, tested against every planet that could be studied, and applied to create a coherent picture of how a solar system works. Neptune breaks almost all of them. Its atmosphere generates violent weather from an energy source that the standard model for ice giants cannot fully account for. Its magnetic field is tilted and off-center in ways that no clean interior model reproduces. Its interior contains irregular dense pockets that suggest ongoing geological activity in a world supposed to be geologically dead. Its ring arcs maintain coherence against mechanical forces that should have destroyed them. Its storm systems reverse direction in ways no atmospheric model predicted. Its cloud cover vanishes and returns on a schedule tied to the sun in ways that require a mechanism nobody has confirmed. When a single observation contradicts a model, scientists revise the model. When multiple independent observations from different instruments and different research teams all point to problems in the same framework, the framework itself requires examination. Neptune is producing that second kind of pressure. The planet is not presenting one anomaly for scientists to explain. It is presenting a convergent set of anomalies across every major system, atmosphere, interior, magnetic field, rings, moons, and gravitational influence on the outer solar system. They all point toward an underlying reality that current models fail to capture. This is scientifically uncomfortable in the best possible way. Discomfort in science means the boundary of understanding has been found. Anomalies that resist explanation are exactly where the next generation of discoveries lives. The history of science is full of examples where a single stubborn anomaly, one result that refused to fit the accepted model, eventually forced a revolution in understanding. Mercury's orbit refused to fit Newtonian gravity, and the resolution was Einstein's theory of general relativity. The photoelectric effect refused to fit classical wave theory, and the resolution was the discovery of quantum mechanics. Neptune may be that kind of stubborn anomaly for planetary science, a planet that refuses to fit the model, not in one way but in many, simultaneously from every instrument that examines it. The resolution, when it comes, will almost certainly require new understanding of what happens inside ice giants. It may require revisions to how scientists model planetary formation and migration. It may reveal new physics about the behavior of matter under the extreme pressures found in planetary interiors. Whatever it reveals, it will change how every ice giant, here and across the galaxy, is understood. The next step toward that resolution begins with asking what, exactly, could be driving all of it at once. The history of planetary science offers a reassuring precedent. When Voyager 2 flew past Neptune in 1989, scientists expected a quiet, unremarkable world. What they found in just a few hours of flyby data overturned decades of assumptions about ice giants. Now, 35 years of increasingly powerful telescope observations have multiplied the anomalies far beyond anything Voyager 2 hinted at. Every additional year of data from Hubble, Webb, and ground-based observatories adds another layer to the mystery and another constraint on whatever explanation will eventually emerge. The answer, when it comes, will have to account for all of it at once. The storms, the magnetic field, the interior, the rings, the glow, the chemistry. A demanding set of constraints is precisely what forces science forward. Every discovery about Neptune points toward a center. The wind speeds that should not be possible. The storms that reverse direction. The cloud layer that vanishes on a solar schedule. The stratosphere that cooled for 15 years and then rapidly rebounded. The South Pole that heated up without any external cause. The off-center magnetic field. The irregular interior full of dense pockets. The unidentified glow in the southern hemisphere. The trace gases riding up from below. The ring arcs refusing to dissolve. These are not separate mysteries. They are symptoms. And symptoms this numerous and this interconnected point toward a single underlying cause that scientists have not yet identified or named. The best current candidates each explain a portion of the evidence. Internal heat pulses from phase transitioning material in the deep interior could explain the atmospheric temperature swings and the excess energy output. An irregular, partially active core could explain the off-center magnetic field. Vertical mixing driven by internal heat could explain the trace gas distribution and the dark spot chemistry. The solar cycle connection could explain the cloud disappearance. But no single model ties all of them together cleanly. When scientists try to fit every piece of data into one framework, the framework always needs exceptions. Something is being missed. There is a class of phenomena in planetary science that scientists call emergent behavior. This is when a complex system, one with many interacting parts, produces effects that cannot be predicted from studying the individual parts alone. The interactions between components create something new at the system level. A behavior that no single component generates on its own, but that the system as a whole produces. Neptune may be demonstrating emergent planetary behavior on a scale that has never been observed before. The interplay between the irregular interior, the off-center magnetic field, the internal heat distribution, and the atmospheric dynamics may be generating effects that none of those systems would produce in isolation. The whole is behaving differently from what the sum of its parts would predict. If that is true, understanding Neptune fully will require not just better data about each individual system, but a new framework for how those systems interact with each other across the entire planet. A framework that does not yet exist. Scientists who work on Neptune describe a feeling of standing at the edge of something significant. Not a single discovery waiting to be made, but a shift in understanding that could reshape what it means to be a planet. An ice giant at the edge of the solar system, 2.8 billion miles from the sun, in the dark, generating phenomena that 3 decades of observation have catalogued but not explained. Whatever is driving Neptune, it has been running for 4.5 billion years. It has outlasted every model built to describe it. And it will keep operating, indifferent to the limitations of our instruments, until we build something capable of getting close enough to finally see it clearly. Neptune is waiting. The understanding is not yet built, but the question is now clear enough to pursue. 4.5 billion miles from the Sun, an ice giant is generating phenomena that no model fully predicts, at a distance that makes direct investigation almost impossibly hard. The universe does not make its most interesting places convenient to reach. When humanity finally sends a mission close enough to read what Neptune is actually doing, the answer will almost certainly rewrite what it means to understand a planet.